Welcome to Science Snippets, Fun Facts and Trivia. Today, we bring you: do black holes disappear? How Hawking radiation reveals their fate. Have you ever thought about whether a black hole could actually disappear? It sounds crazy, right? Something that massive, just fading away. Well, that's exactly what Stephen Hawking suggested back in 1974. He proposed the existence of what we now call Hawking radiation, a phenomenon that might explain how black holes can slowly vanish over time. But before we dive into how that works, let's quickly talk about black holes themselves. Traditionally, black holes have been viewed as cosmic vacuum cleaners, pulling in anything that comes too close, even light, because nothing can escape their gravitational pull. It was assumed that black holes were essentially eternal. Once something gets sucked in, it's gone forever, right? But Hawking's theory flipped that idea upside down. Hawking discovered that black holes, despite their immense gravitational power, might not be completely sealed off from the universe. In fact, under certain conditions, black holes could slowly radiate away their energy. This idea of black holes emitting energy was revolutionary, because it meant that they might eventually lose enough energy to disappear entirely. So how does this all happen? Now that we know black holes can potentially disappear, how exactly does this Hawking radiation work? It all starts with quantum mechanics, which governs the strange behavior of particles at the smallest scales, near the event horizon of a black hole, where the gravitational pull is extreme. Quantum mechanics comes into play in a big way. According to quantum theory, empty space isn't really empty. It's constantly filled with tiny particle-to-particle pairs, popping into existence. These pairs usually annihilate each other almost immediately. But near a black hole's event horizon, something different happens. One of the particles gets sucked into the black hole, while the other escapes into space. The particle that escapes becomes what we call Hawking radiation. But here's the key for that particle to escape. It has to borrow a little energy from the black hole itself. When this happens repeatedly over time, the black hole slowly loses energy. And since energy and mass are equivalent, this process causes the black hole to shrink ever so slightly. But don't expect black holes to just vanish overnight. For a black hole to completely evaporate, it would take an incredibly long time, far longer than the current age of the universe for most black holes. The larger the black hole, the slower the process. In the end, though, if nothing adds mass to the black hole, it could eventually evaporate completely, leaving behind, well, we're not exactly sure. Some theories suggest a tiny remnant might remain, while others say the black hole might vanish without a trace. But one thing's for sure: Hawking radiation means black holes aren't the eternal cosmic monsters we once thought they were. So, if black holes can evaporate over time, what actually happens when they get close to disappearing? As a black hole loses energy through Hawking radiation, it gets smaller and smaller. But here's something surprising: as the black hole shrinks, it actually starts to radiate faster. That's because smaller black holes emit more Hawking radiation than larger ones. This creates a kind of feedback loop. As the black hole loses energy, it shrinks, and as it shrinks, it emits even more radiation. Eventually, in the very final stages of its life, the black hole could be radiating so much energy that it essentially explodes in a burst of light and particles. This end phase is often referred to as the black hole death. When the black hole has lost almost all of its mass, and only a small amount of energy is left to radiate away, some scientists predict that the black hole might vanish entirely, leaving nothing behind. Others think there could be a tiny, stable remnant, too small to continue evaporating. This remnant would be incredibly dense. But what it would be or how it would behave is still a mystery. What's also fascinating is that this process could take an unimaginable amount of time. For a black hole the size of the Sun, it might take more than a trillion years to evaporate completely. Although no black holes in the observable universe are close to this stage. Yet, understanding this process helps scientists explore bigger questions about the ultimate fate of the universe. Could the slow evaporation of black holes be tied to the universe's long-term future? And what about the matter and energy that fall into black holes over their lifetimes? Where does it go, and is it lost forever? These are still open questions, but the study of Hawking radiation brings us one step closer to understanding how black holes live and die. Hawking radiation is not just about black holes. It also plays a crucial role in modern physics, especially in the ongoing effort to unite two seemingly incompatible fields: general relativity and quantum mechanics. General relativity, which describes gravity and the larger scale structure of the universe, works extremely well when dealing with massive objects like stars, galaxies, and black holes. On the other hand, quantum mechanics focuses on the behavior of particles at the smallest scales, where the rules of physics seem to be completely different. These two pillars of physics don't always fit together smoothly, especially when we try to apply quantum mechanics to objects with extreme gravity, like black holes. This is where Hawking radiation becomes so important. It's one of the rare instances where both quantum mechanics and general relativity come into play, providing a bridge between the two. But Hawking radiation also leads to one of the biggest mysteries in modern science: the black hole information paradox. In quantum mechanics, information is never truly lost. Even if something changes form, the information about it still exists somewhere. But black holes seem to challenge this. That is, if a black hole evaporates completely, what happens to all the information it absorbed over its lifetime? Is it lost forever, or does it somehow escape? This paradox has puzzled scientists for decades, and many theories have been proposed to resolve it. Some suggest that information might be encoded in the Hawking radiation itself, while others believe new physics might be needed to fully understand what happens to information inside a black hole. Hawking radiation also forces physicists to think about the fundamental nature of space, time, and matter. It raises questions about the fabric of the universe itself, and how the laws of physics behave under extreme conditions. Even though Hawking radiation hasn't been directly observed yet, its theoretical implications are profound. It continues to drive new research and inspires innovative ideas in theoretical physics, pushing us closer to a unified theory that might one day explain the deepest mysteries of our universe. To wrap things up, black holes, once thought to be eternal cosmic monsters, are not as permanent as we once believed. Thanks to Stephen Hawking's groundbreaking theory, we now understand that black holes can slowly lose energy through a process called Hawking radiation. This radiation causes black holes to shrink over time, potentially leading to their complete evaporation. While this process takes an incredibly long time for most black holes, it changes our fundamental understanding of how these mysterious objects behave. The discovery of Hawking radiation also reveals something much deeper about the universe. It forces us to confront questions about the nature of space, time, and information. What happens to the matter and energy that black holes consume? Could this radiation hold clues to solving some of the biggest mysteries in physics? like the unification of general relativity and quantum mechanics. And while no black hole in our universe is expected to evaporate anytime soon, this theory helps scientists explore the ultimate fate of black holes, and possibly the fate of the universe itself. Black holes, it seems, are not the eternal, unchanging objects we once thought they were. Instead, they might have a finite lifespan, slowly losing their energy until one day they disappear entirely. It's fascinating to think that one of the universe's most powerful and mysterious objects could simply vanish into nothingness, leaving behind even more questions for us to explore. If you found this video helpful or interesting, please give it a thumbs up and subscribe to the channel.